Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Implicit Differentiation. Be sure again to be an active learner as you're watching this video. Up to now, we have dealt with functions expressed in the form y equals f of x. That is, functions in which the dependent variable y is expressed explicitly in terms of the independent variable x. That means we have solved for y. However, not all functions are expressed in this form. Consider, for example, the equation that is shown here. We don't have y by itself. Now, this equation does express y implicitly as a function of x, and we can solve this equation for y. And if we do that, we would factor the y out here, move the other stuff to the other side, and then we divide both sides by the coefficient of y after we factored the y out, and we can get an explicit equation for y in this case. But if we consider this case, it's very difficult to do that. In fact, I would not want to do that myself. So if certain restrictions are placed on x and y, it does define y as a function of x, and we assume that that is the case. But in this instance, we'd be hard-pressed to find y explicitly in terms of x. The following question arises naturally. How do we compute dy dx in this case? As it turns out, thanks to the chain rule, a method does exist for computing the derivative of a function directly from the implicit equation defining the function. This method is called implicit differentiation and is demonstrated in the next several examples. Okay, so suppose we have y squared equals x and we want to find dy dx. Well, we're going to differentiate both sides with respect to x. So we're taking the derivative of x with respect to x, which is going to be 1. That's going to be 1. But then we're going to take the derivative of this side with respect to x. So by the chain rule, we have to take the derivative of this first with respect to y and then with respect to x. So you see what happens is the derivative of y squared is going to be 2y then times dy dx by the chain rule. Therefore, this side becomes this after I take the derivative. This side becomes this, and then I can solve for dy dx by dividing both sides by 2y. Before considering other examples, let's summarize the important steps involved in implicit differentiation. And here we assume that y is a function of x and dy dx exists. So what we do then is we differentiate both sides of the equation with respect to x. Make sure that the derivatives of any term involving y includes the factor dy dx, because you have to use the chain rule to take the derivative with respect to x. And then you solve the resulting equation for dy dx in terms of x and y. So here's our second example. We're to find dy dx for this function. Notice that there is a bunch of terms that have y in them, and we'll have to be careful of them. And when we take the derivative of 8, that's going to be 0. So we differentiate both sides of the given equation with respect to x, and we get 0. And we're taking the derivative of each term with respect to x. So this is going to be 3y squared dy dx. This is just going to be dy dx. This is going to be 6x squared, and this is going to be minus 1 equal to 0. Now, we will take the terms that contain the dy dx, put them together, and then factor out the dy dx. We'll move the other terms to the other side, and then we'll divide by the coefficient of dy dx, and we get this. Yes, there is algebra involved in this problem. Here's another one. We're to consider this equation, and by the way, this is the center of the circle rather, centered at 0, 0 and of radius 2. So we want to find dy dx by implicit differentiation, find the slope and equation of the tangent line, in fact. Okay, now we are not solving, we're going to use implicit differentiation. So we take the derivative of this side, so it's the derivative of this, plus the derivative of this, and the derivative of 4, that's a constant, is 0. So this derivative is going to be 2x. This derivative is 2y dy dx. So I can solve for dy dx, and I get dy dx is equal to minus x over y. And that is not defined for y equal to 0. Okay. Now, so the slope of the tangent line at this point, 1 comma the square root of 3, is found by substituting that in. We use this notation. We substitute it in, and we get minus 1 over the square root of 3. Please remember that there's a minus there. It doesn't show up very well, but there is a minus. Okay, and again, we read that dy dx evaluated at the point 1 comma square root of 3. Then what we're going to do is take that point, and we'll say y minus the y coordinate is equal to the slope. Remember, this was negative, times x minus the x coordinate, and we can put that in many different forms. Now, if we were to sketch that, you see that's the blue line, and it is indeed tangent to the top of the circle. Now, even though you could solve this, what happens is you get two answers because you're taking the square root, so it's plus or minus that square root. So you have to decide which function you're talking about. Since we're talking about 1 square root of 3, that's in the first quadrant, that means it's the upper half of the circle that we're talking about, so it has to be plus. And again, note that this notation means that we're evaluating dy dx at the point AB. I'm going to probably ask you to do that more often than other things. And when you are finding dy dx at a specific point, you can substitute those values a and b in before you solve for dy dx. For some reason, students think this is easier. Okay, and let's do an example of this. So we're to find dy dx at this point where x is 1 and y is 2. There's the function. And notice that this, for the first time, we have to be fancier in our derivatives because here we have x squared, a function of x, times y cubed. So this is the product rule that is happening here. So we're going to begin, differentiate both sides of the given equation with respect to x. And we get, now we're going to use the product rule on this. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. Here the derivative of this with respect to x is just 12x. That is dy dx, and the derivative of 12 is 0. But now we have to go back and finish these derivatives. And so what will happen here is the derivative of this is 3 y squared dy dx, and I take that times x squared, so this is what I get at the end of the day. Here I get y cubed, and this is going to be 2x, so I get 2x y cubed. Now I have dy dx on the other side. Now I'm going to have to solve for this dy dx, so I have to move the dy dx's to the same side, or in this case I can substitute 1 and 2 in for y. So I get this is equal to that. Now I still have to solve for dy dx, but you see it is easier. And when I solve for dy dx, I get dy dx is a number, and that is negative 28 over 11. Now here we're supposed to find the second derivative of y with respect to x. Again, notice that we will want to be using implicit differentiation. And notice that right where I'm pointing, that is a product rule because I have x, which is a function of x, times y, which is a function of x. So we're going to differentiate both sides, and again, to find the second derivative, we have to find the first derivative first. So we're going to find the first derivative, so that means we're going to differentiate both sides with respect to x. So this is going to be the derivative of the product is going to be the first times the derivative of the second plus the derivative of the first, which is 1, times the second, minus this is going to be 3y squared dy dx, and that's going to be 0. So I solve for dy dx and get that dy dx is y over 3y squared minus x. Now I am going to take the derivative of this again, now that I've solved for that, and that is going to be the second derivative. So here I take the derivative of this, that's giving me the second derivative. Here I'm going to do the denominator times the derivative of the numerator minus numerator times the derivative of the denominator, all divided by the denominator whole squared. Now the derivative with respect to x of y is dy dx, and the derivative of this expression with respect to x is going to be 6y times dy dx. That is the chain rule minus 1 all over this. And then I start doing algebra, and I can get this expression. But now I can substitute what dy dx was where I have it. So I'm going to take this and substitute it in for this, and do algebra and simplify, and I get this expression. Now I'm going to I often will give you numbers to substitute in, but there still is algebra involved. Algebra, of course, is your friend. And look how important it was for you to have done the simplification before you took the second derivative. And life is a word problem, so here you end up with the output of a country is given by this expression. It's a product of two functions, both of x. And so you're supposed to find the output of the country if $625 billion is spent on labor and $81 billion is spent on capital. So that's just substituting the values in. But then what you're going to do is you're asking by how much should the amount spent on capital be changed if the amount spent on labor is to be increased by $1 billion. Okay, so first we're going to just substitute those values in, and we get this number, and that is $3,750 billion, which is $3.75 trillion. So we want to find the change in y per change in x. That means this is dy dx, when x is 625 and y is 81. So we're going to implicitly differentiate this expression. And so we're dividing all the way through by 10 here. And so when we do that, we're going to be using the product rule on this side, and the derivative of 375 is going to be 0. So here, what I'm going to get is, I'm taking the derivative of the first, which is 3/4 x to the minus 1/4 times y to the 1/4, plus the first, x to the 3/4 times the derivative of the second, y to the 1/4. This is 1/4 y to the minus 3/4 dy dx. Now this is an expression then that I can solve for, dy dx, and I find that dy dx is equal to this after I simplify. And then I substitute the values in. I could have substituted them in earlier, and I get this as an answer. So to keep the output at a constant level of that, the amount spent on capital should increase by this amount, this 0.3888 billion, if the amount on labor were to be increased by 1 billion. Now, this is actually something economists do study, and the negative of that derivative is called the marginal rate of technical substitution. And in general, the marginal rate of technical substitution measures the rate at which a producer is technically able to reduce one input for a unit increase in the other input while maintaining a constant level of output. And this allows them to make decisions about how to manage the economy. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.